I'm Corey Isaacson. I'm going to be giving the talk this afternoon. We're going to be talking about scaling your database in the cloud. Anyway, I want to just go through a little bit about what it takes to do scaling of your database in the cloud. There's a lot of challenges. I'm sure all of you know that, and that's why you're here. Just curious, by show of hands, though, how many of you have ever had a database performance problem? Good, it's unanimous. Me too. Me too. So databases are challenging, right? Anything that you do and anything that you do in software always seems to be tied up in the database. And this is why I got so interested in this field and why we decided to basically do the startup that I'm working on now in our company. And so we'll tell you a lot about a lot of the challenges and what's involved and how you solve those challenges. And really the goal today is really that you learn something that you can take away and apply, I hope, right away. You should be able to use this information in a practical format. We'll also have plenty of time for questions afterwards. I have business cards there too, and will be available after the session if you have any more specific questions. So let me just tell you a little bit about our company and about myself. I actually wrote a book called Software Pipelines a few years ago, which is all about how you scale applications. And the whole theory of the book is that you can relate software and transaction flow to fluid flow or water, is the idea. And it actually worked out to be a pretty easy way to understand and compare fluid mechanics to software flow, and it makes it very easy to predict where bottlenecks are. But again, a big point in the book is that no matter what you do in the software flow, if you do things in parallel and how do you get things to scale, the database always seems to be the bottleneck at the back end, and how do you really approach that? So as an offshoot of some of this work, we have a product called DB Shards. A lot of people can do sharding on their own, though. I want to stress that if you have a simple application, there's a lot of the techniques we'll talk about today you can just use. I'm also, of course, we do a lot of work with RightScale. Just so you know, we are now supporting with RightScale 3 of the top 50 Facebook applications in the world actually run DB Shards and RightScale together. So we're very, very happy about that. Some game companies, some other companies, we'll talk about some of those as an example as we go through the talk. So again, I want to keep it very practical. At the end, we'll take questions. We can make sure that everything is clear. So one of the things about databases is that they get bigger. Right? Everybody knows that, right? The world is getting bigger as far as data goes. I recently had the pleasure of visiting China. And I can tell you that I don't think we've seen anything here yet as far as what's really going to happen. They already have twice as many internet users as we do in the United States. So it's pretty impressive, actually, and they're not finished yet. Right? So they have a tremendous amount of growth, and everything there is going to be huge. If you think of just buying, airline tickets or anything like that, they just have so many people, in the country that it's just going to be very, very big. But again, in the U.S. too, I think we're all seeing the same thing. As we're dealing with social networking, we're dealing with huge amounts of data, very, very large data sets, data analytics, all kinds of different things that are causing databases to grow. And when they grow, they do exactly one thing: is they get slower. It's very predictable that your database is going to get slower as it grows. So why do they get slower? Because you have a lot of user contention, you have locking, those kinds of things make a big deal in slowdowns. You have limitations on the number of connections you have. But a big part of it that a lot of people are not as aware of is index depth, what we call index depth. As a database or a table gets bigger, and if you have, let's say, 2, 3, or 4 indexes on that table, all databases, doesn't matter what kind, use pretty much the same type of index, which is a B-tree index. And a B-tree index gets more complicated the more rows that are in it. And so you end up with more contention on the index, and all of a sudden your write speeds start to go way down. And we'll show you some examples of exactly how that happens and what you can do about it. Table sizes, of course, but I/O bottlenecks. That's a huge problem, right? Databases are I/O bound, and so every I/O bottleneck is a big, big issue for databases. Now, you're all here at a cloud conference, so I'm assuming that most of you either are running in the cloud or you want to run in the cloud. And you may have noticed that the I/O in the cloud is not as fast as what you have in other environments. So we've actually measured it, and we know pretty well how that works. So, and we want to say that these challenges apply really regardless of the hosting environment, but of course we're most interested in the cloud, and that's what we'll be talking about today. So when you look at challenges in the cloud environment, what we have is the cloud is very, very attractive. Why? Because it's a service-based environment, and effectively what you can do is you can have it be flexible. You can scale up and down with your needs. That works fine. You don't need as much dedicated IT staff to run in the cloud, so that's really good. You pay as you go. It's good for small companies that are growing, a lot of bigger companies too. But you may have noticed that cloud services fail once in a while. Anybody seen a cloud failure? Yeah, okay. Just about the same as database performance, right? So we've seen everything from partial network outages. Sometimes they're very intermittent because we host a lot of and manage and help our customers manage a lot of database servers in the cloud. We actually see everything, right? Because our databases are running 24/7, and any issues are going to be noticed very, very much by our support staff. So we have server failures. The servers in the cloud, I don't know if you've ever tried to run a server for a couple of years or something like that, but your chances are not so good that it's going to keep going perfectly for that amount of time. Disk volume issues, we've seen disk volumes just totally disappear. We've seen them slow down. One thing we noticed recently is that with elastic block storage in Amazon, the I/O rates will vary. Right? We see peak I/O rates of around 400 or 500 operations a second. That's pretty much typical. Things run pretty nicely when we can keep it around that range, but sometimes they just go down to 100, for whatever reason, because things get busy or whatever. And the reason is, of course, that cloud resources are constrained because it's not just you're sharing them with other people, right? So that's a big factor as well. So we have these limits with the I/O rates, and we call this the cloud I/O barrier. This is one of the key things that we actually do. So let's look at a typical application architecture and look at how we put this together. Most applications are set up something like this. You have the load balancer tier, you have the application server tier, and you have the database tier at the bottom. And so we're going to talk about what it takes to scale each of these so that we can really look at how this fits with the database technology. So scaling load balancers is really easy. Why? Because they're stateless, right? All they're doing is routing traffic to one or more application servers. You can use different kinds of redundancy for them. You can even use DNS so that you can do it across data centers or across regions or even across clouds if you wanted to, actually. And if one goes down, fail over to another, who really cares? You're not going to lose anything. Application servers are easy also because why? They are also stateless. They're not really keeping any state. Some applications are keeping session state and things like that, but most of the application servers you'll find really don't keep anything that's critical, and the worst case is if one goes down, a user might lose something, one user, but they'll come back and everything is fine. Scaling the database tier, though, is anything but easy. It's very, very hard. And the reason is, of course, databases are stateful by definition. That's what they do, is they actually track and keep state. That's their job. So because of that, you get large integrated data sets. We can have tens of gigabytes to terabytes, of course. They're very difficult to move and reload. I always liken moving a big database like moving a freight train across the country, right? You have a ton of stuff and you have to move it, and it just doesn't go very fast. Again, we talked about the fact that they're I/O dependent, so they're very adversely affected by any sort of cloud service failure, right? Network, I/O, any of those things I talked about will hit the database harder than anything else. And if one goes down, you don't want to come to work that day, right? That's no fun, right? So what we know is that databases really form the last mile of true application scalability. You're not going to get there. Every key application today has a database at the bottom of it, and if you can't scale the database, you can do a lot of other magic, but this is really going to be a roadblock. So the first thing we really recommend when you're looking at this is you should really look for and try to find simple optimizations in your database to do that before you actually look at a scaling strategy. And why we say that is very often you'll see, we see this all the time, that an application is getting slower or is having some sort of problem, and what really happens is that sometimes maybe there's some tweak you can do in the application, maybe there's an index you can add, maybe there's something simple like that that will basically get you through a certain period of time. But even with doing that, at some point you're going to be constrained, especially with write volume. So how many of you have applications that have database writes? I'm sure they all do, right? But how many are write intensive? right? And this is the trend now, as we see more and more applications that are write intensive. Any of the social networking type of applications, any of the analytics applications, we see a tremendous amount of database writes, and those writes are purely constrained by I/O and how fast the database can work and index speeds and all of those things. So what we really do recommend is that you implement a follow-on scalability strategy, and you should start working on that, we think, immediately. And why? Because we get a lot of calls when it's kind of late, right? And we help everybody, and it works out fine. But it's much, much better if you actually work out your scalability strategy up front before it's an emergency. That's a much, much better strategy. So there's other challenges with databases. Databases, you want transactionality, typically. You would like things to be either work or not work if you're writing various records. The other thing you want is you want them to be consistent. You want to preserve relationships. We're going to talk a lot about related data. If you notice, any data in the world is related to other data. Nothing means anything without other information, right? We're all here in this seminar today, in this talk, and so that's a relationship right there, right? All of us are, it's a one-to-many relationship from this seminar to each of us here in this room, right? The chairs are related to the floor, the lights are related to the ceiling. You can see how all of these things are related. It's the way the world is built. I have a very relational view of the world, the way I look at things. But it's true, actually, is when you're modeling things, you're actually copying that information, right? And so it's very, very important to preserve referential integrity, right? It wouldn't do so good if you had a chair and no floor. That would be kind of difficult, right? It's not going to work too well. So we also have operational challenges with databases that are very important. We need failover when something bad happens, but we also need failover when you have to do maintenance. Databases take work. You know, they don't just keep running well. We have actually had customers that have not been able to do any maintenance on their database for years, literally because they were 24/7 operations and they knew it would take days to do it and they couldn't take the system down that long. And there was just no way to actually effectively do it. So maintenance is very important. Lifecycle, backups. Backups are very important. We like to have backups with databases and make sure we can restore things. So I want to talk about an example. We have a case study, which is a company called Family Builder. Family Builder is one of the top 50 Facebook applications in the world. They make a simple family tree application. It's kind of cute, actually. You know, a lot of people really, really like it. As a matter of fact, when we started working with them, they had about 20 million users. Today they have over 50 million users. They get 100,000 new signups every single day. Every single day. And they had a lot of problems with their database when we got to them. They definitely waited too late, but so we, it was kind of an emergency, but we were able to help them scale. But the key thing that we noticed about it is this is what the I/O barrier was actually coined. That term was coined by their CTO, and this is what their CPU graph actually looked like when we started with them. So for all of you who know what RightScale graphs look like, you know that red is bad and blue is good. So the red is the I/O wait. It means it's waiting for a disk. That's what their database was doing. And there's an old joke from back from the mainframe days, which is that all CPUs wait at exactly the same speed. Doesn't matter how fast they are. So we looked at this and we said, this is a real problem. Well, what did this, we know it's a problem system-wise, right? But let's look at what it did to their actual business. This is a very successful company. A lot of people really like this application. So what would happen is every time they would do marketing, the system would break because the database would get overloaded. So it would crash, basically. So they actually, over a period of years before we started working with them, actually tuned it to where they never did too much marketing at a time. So they could never grow too fast. And it really was a lot of arguments between the technical people and the business people, believe me. They didn't really like it, right? And so this was really constraining their entire operation. So we'll use this example and we'll show you actually how we solved it. So what we know is that databases slow down, of course, as they get larger. And basically, it's not a linear slowdown. Unfortunately, it would be nice if it was very, very predictable and you could actually predict it and say, okay, in 2 months I'm going to be in trouble. But it just doesn't work like that. What happens is the performance actually kind of, goes like in a hockey stick like this, as it really, really slows down badly. And here's an example. We actually took a complex database with about 12 indexes, so we wanted to have more indexes to show this idea of the index degradation. And what we did is in ODB, we actually loaded a gigabyte of data in about a minute. We loaded 3.5 gigs in 12 minutes. That's still okay. 39 gigs took 10 days, and we finally gave up. We quit waiting. So the point is you can really get into serious trouble very quickly and not have it be predictable. And one of the key things we recommend you do is watch that I/O wait time, because that's the first sign that you're going to be in trouble soon. So if you see that starting to happen, don't wait until the graph looks like the Family Builder one. So now these challenges, they apply to all types of databases. It really doesn't matter what kind of database you're using. Of course, traditional databases like MySQL, Postgres, Oracle, they're all I/O bound, multi-user and lock contention, high availability, lifecycle management. Of course, that applies there. But also, it applies to NoSQL, NewSQL, column databases, caching. There's lots of different kind of databases out there, right? And one thing we know is that we love seeing lots of different kinds of databases. Why? Because they're all better at certain kinds of things than other products are. And so you want to be able to use the one that actually fits the job that you have. But it really doesn't matter as far as these issues, because they all are affected pretty much similarly. With NoSQL and NewSQL, you have reliability issues, limits of a single server. Remember that these databases, most of them are single-threaded. And a lot of people are not aware of that when they start to use them. You can do really, really fast writes with a NoSQL database, but when you do, they're single-threaded, which means if you have one bad transaction that takes 30 seconds, everybody waits for 30 seconds, right? So it can be very, very dangerous if you're not aware of that. You have to do dumps to disk, high availability, all the same issues. So no matter what type of technology, big databases are just hard. They just are difficult to manage. They take a lot of work. Elastic scaling is a real challenge. Degradation is a certainty. You know your database is going to get bigger. You know it's going to get slower. There's no question about that. Again, we have application-specific database requirements, or sometimes there's maybe bugs where an application developer does something maybe they shouldn't have done, and that could actually have a serious effect too. Have you ever seen a developer who writes a query that's, let's say, has a Cartesian product, or they forget to put a join clause in, and all of a sudden they're bringing back 10 million rows, and it doesn't work so well. So one thing we really stress is that sound database design is key, right? It's very, very important. So how many of you are familiar with entity relationship modeling and traditional database design? Okay. We still really believe in that as a way of doing things, because if you understand the relationships, I can see there's some other fans of that too. I've been doing it for a long, long time, and it's the only way I know how to understand and actually define a database. And one of the things that we see happening is that with NoSQL and the advent of it, some of these products are really cool. The APIs are simple, they're a lot of fun, and it looks like, hey, I can just do things without structure, correct? I can just do it kind of any old way. Well, I'll tell you that there's something that people don't realize, is that those relationships in your data are not going to go away just because you have a NoSQL key value store. They are not going away. You still have them. Guess who gets to manage them if you don't have a relational database behind you? The developer does. That's right. And so if you have 10 developers on a team and you have to enforce referential integrity, guess what? You have to get 10 people to do it right. So it's almost more important to have a really great database design with a NoSQL database than it is with a SQL one. Now there are some very simple use cases we've seen people have where they're just logging lots of the same information, and it's not that complicated. But as soon as you get into any sort of complex social networking or analytics application or anything like that, you are talking about relationships. They don't go away just because of this. So we came up, it's a little bit of a joke, but true enough, is that the laws of databases, right? And the laws of databases are that small databases are really, really fast, big ones are really, really slow, so keep them small, if you can do that. And people ask me always, well, what's the right size for my database, right? And so we say, well, when's the last time it ran the way you liked? That's the right size, because it does vary by application. So what's the answer now to all of this? The answer is something called database sharding. It doesn't matter which of these technologies, what kind of database you're using, the only way to scale a database effectively today is database sharding. And I'll explain exactly what we mean by that. But it really is what, there are different names for it in different companies that have different products and so on and so forth, but they're all doing the same basic technique. So database sharding is effectively horizontal partitioning of your data. This is the definition, the technical definition from Wikipedia if you want to look it up. But I'll give you a simpler definition that we like, which is basically you start with a big monolithic database, you break it into smaller databases across many servers, and you use a key value to do that distribution. Usually with something called consistent hashing, which means you're basically doing some sort of modulus algorithm or something like that, where you're actually spreading the rows out. So if you looked at that picture before, you'll see that if we were doing customer data, let's say that this is our customer ID at the bottom, you'll see that customer 1 is in shard 1, customer 2 is in shard 2, 3 and 4, and so on. And that's really the simplicity of actually how database sharding works. And again, it doesn't matter what technology you're using. If anybody claims that they have database scalability, they're doing this. In one way or another, this is how it's working. So what's the key to database sharding? Share nothing. That's the most important rule. Read any paper on scalability and performance in computer science, and you know that if you share any components in an array of computers, you're going to slow things down. So what you want to do is you want to have your servers each be as independent as possible or completely independent, and that's really what we recommend is a total share nothing architecture. So let's now look at the database sharding architecture and look at some of the pieces and components that are actually involved. So what we have is we have the application server tier. So that's the place where your application actually runs. It could be PHP, it could be Python, it could be Java, it could be anything you want. And effectively what we have is we want to have a client, which is the driver component for the database. And this is the way we really like to see it. And the driver is intelligent and it understands the sharding scheme. And then we have multiple shard servers, each with their own database. And so each one is independent and operates independently. And what happens is you get tremendous scale up and speed difference when you do this, because each database now can breathe and do its job very, very effectively because it's defined in a size that actually makes sense for that particular engine. And that, like I said, could vary a lot based on the engine and the type of application you have as well. So in some cases, we see architectures that look more like this, where there's actually a proxy server between the application server tier and the database tier to actually do the sharding itself, and the sharding is done in the proxy tier. We don't like this as well unless you go very, very large. If you go large, then this is a requirement. But the problem is that this makes more servers to manage, number one, so there's more failure points. It's more complicated. It's going to be slower a little bit because you're going through another layer. So if you can avoid that, then that's better too. So how well does it work? So one thing we know is writes are the bane of databases, right? That's the most difficult part of database transactions is write speeds. And like I said, we see applications becoming more and more write intensive all the time. So what we know with database sharding is that we actually know that writes are linear. So in other words, if I have one shard, this is an actual MySQL test in the cloud, we were getting about 2,500 writes a second with one. With 4, we were getting 10,000, almost exactly a straight line graph. And you can keep just going and going and going with this. It works out incredibly well. Of course, it depends on how big your writes are and things like that. But I remember when we actually started working on DB shards in the very early days of our company, we wanted to do some tests to see if this actually worked. And I work with a chief architect. His name is Andy Grove, a brilliant guy, not the Andy Grove you're from Intel. But we tell people we have the most famous chief architect in the world anyway. But anyway, he ran some tests, and it was he's British, so he's a little bit conservative. But he came back to me and he says, sharding works. It was really funny day. But anyway, so we know that again you get linear performance in writes. With reads, you can get better than linear performance if you do the right job, and I'll show you why. So sometimes you can do even better with reads. So why does this really work? The reason this works is we're actually changing the balance of CPU and memory compared to the database size. That's the whole goal, is if we have more CPU available and more memory available, then the database works better. Why? Because database engines, particularly the proven ones that have been around a long time, are extremely good at caching things, at reusing things. I mean, they've had years and years and years of tuning all of this. So if you give a database enough room to breathe, it can really perform much, much better. And memory is 50 to 100 times faster than disk, especially in the cloud. So you can get tremendous speed ups just by getting more of the data. Especially, we want to have at least enough memory per shard to get the indexes in memory. If we can at least do that, we know we're going to be in really, really good shape. Remember we talked about the index tree complexity and depth? Well, if the index fits in memory, all of that can be done 100 times faster, that logic, than if it's on disk. So if the index gets too large and it has to go to disk, it's almost like disk swapping in your operating system. It's really a very, very similar effect to that. So we want to reduce the size of the index trees. That makes writes dramatically faster. This is probably the single biggest benefit of actually doing database sharding. Okay? We also, of course, have less contention. We don't have locking anymore problems between users because, user A could be here and user B could be here. So the locking windows are shorter and everything works. Transactions go faster and everything seems to be better. One thing we've seen in the years, I've worked on many, many applications in my career, and what we know is if you can keep every single database operation sub-second, you're going to pretty much be okay. And as soon as you get one that's not, then you're not okay. So this is really what helps with sharding, is we can make that much, much better. The other thing, though, is we talked about reads and how you can actually have better than linear performance with reads. It's because you can use intelligent parallel processing, because why? You can do things across all the shards and then roll up the results. So our technology does this, but you can do this yourself as well. And so this is a very, very effective technique. And we had one customer where we ran some tests with them. They were doing all analytics queries. They were doing crawling lots of web pages and doing analytics queries against them, and they had hundreds of users pounding the database. And we were actually able to get a speed up of 100 times performance with only 6 servers for what they did, because the databases were so much smaller and those complex aggregate queries could happen so much faster. So it's very, very effective. And we call that, we have a technical term for that, we call it GoFish. It means if we don't know what shard to go to, we actually go to all the shards and run things in parallel. So again, the idea is we distribute the queries out, and I'll show you how this works a little more later. We run them on every server and then roll up the results. Then, it goes much, much faster. So what's the goal of all of this? Keep those CPUs busy and productive. That's what we're after. So I'm happy to say that this bottom slide is what Family Builder looks like today. They are running just on 4 shards, by the way. They've been running on this architecture for over 2 years now. You can see the above graph, which is what they looked like before. So just to give you an example, they have more than doubled their user base. They have, again, 100,000 new signups today. I think that's about double what they had when they started this. And they've been fine on 4 shards for 2.5 years. As a vendor, I was really hoping they would need more shards, but it's working just fine. So, but you see we have a nice, lots of user CPU and very, very little I/O weight. That's exactly what you want to see. And again, you can use this to predict problems, because if this graph starts to look more like that graph, you want to move quickly. That's the first real warning sign that you're going to see. So let's talk again about the different types of databases. So we're all familiar with relational databases. How many people here are using relational databases today? Just about everybody. Okay. So we know about them. They're using the SQL language. They're very, very proven, durable, dependable. Right? They've been around forever. Really, it's a very, very proven technology. But we also have NoSQL and NewSQL databases. How many people are using NoSQL in their applications? Oh, good, about 1/3 of you. So it's good. I see more and more people when I give these talks starting to go after NoSQL databases. So there's lots of different kinds of databases that fit in this category. The NewSQL term is kind of a term, a catch-all that people are starting to use now to cover all of this. But the idea is you have in memory, you have memory cached to disk. Again, they're single-threaded, so you have to be careful of that. Many of them are. But those are the real speed advantages. They're using memory better, and because they're doing single-threaded writes, what happens is that they just do the action and get done. Whereas traditional relational database is multi-threaded, meaning it's handling many user requests. It has to be able to back things out. There's a lot of overhead that goes into that, and that's why you see some of these tremendous performance improvements with the NoSQL databases. So again, there's key value store, document database, hybrid databases. We're seeing all kinds of things. But there's one thing I want to point out about this is that for any of you who've been watching all of this, the NoSQL and NewSQL databases are starting to look a lot more like relational databases as time goes on. Well, how come? Because relationships exist and data has relationships, and you can't get away from that, right? The other thing is, so how do they introduce relationships? By adding indexes. What are the indexes? B-tree indexes, the same thing that has been done for 25 years, right? So it's not really all that different, right? And for any of you who ever worked in the mainframe era, you know, way, way back, if you look at how early mainframe databases looked and worked, they were a lot like NoSQL databases today and how they were architected. It was actually a very, very similar approach if you actually go back and do some study on that. So the point is, there's really no new tricks. I just want to point that out. But it does mean that a database could be optimized for a certain type of operation versus another type of database. That's very true. Very, very true. Especially when you're talking about in-memory databases or you know, key value stores can be very, very convenient. But also, I don't know if any of you have worked with columnar databases, but those can be incredible if you have certain types of analytic workloads. You can get tremendous speed ups if you use those. We're starting to see open source entrants and other things like that as well. So I want to just talk about the different kinds of sharding. There are two basic sharding approaches in the world. One is we call Blackbox, and the other is relational. They both use exactly the same technique where you're sharding the data based on a key, usually consistent hashing, modulus algorithm, something like that. There's no mystery here. I don't care what product you're talking about and what you use, they're doing it that way. So what's the difference between these two types of sharding though? Because it is important for you to understand it based on evaluating which product you're going to use, because it depends a lot on what your workload looks like. A black box sharding is effectively automatic. And what that means is black box sharding takes a key value, let's say the primary key of every table is one example, or the key of a key value store. And it's basically going to automatically shard across n number of nodes, no problem, right? So if you look at Cassandra, you know, MongoDB, those are all doing automatic black box sharding, right? But there are some products that have attempted to do this with relational databases too that are out there. So the key difference is when you're doing black box sharding, it's great because why? It's automatic, because everything is sharded automatically evenly. If you have 20 tables, they're all sharded. You know, you could have a customer row here, their order row could be in another shard, some other attribute could be in another shard for them, right? So it just splits everything evenly and it's completely automatic. You don't have to pay any attention to it at all. And so that's the real appeal, is because it's very, very easy. And this is fine if you're doing simple, non-indexed queries and information. Because why? Let's say you have all these rows spread all over, you know, these different servers. Now you have to add an index. Well, guess what? The index is going to be sharded too. So now what happens if anybody have to ever bring back a list of records in their application? More than one? Like let's say I have a customer and I want to bring back all their orders or something like that. A very common requirement, right? So now what do I have to do in a black box sharding scheme is now I have to go hunting all over the network to reassemble that list, right? So if I have a customer with 10 orders, literally those 10 order rows could be in 10 different shards. And if I have to use an index to do it, which I probably do, the index could be in 10 different shards. So now I have to go to 10 shards to find the index rows, and then I have to go find which rows those are, and then go back and get them all, right? You can see that it becomes very, very cumbersome. So if you're reading and writing single things, black box sharding is like totally fine. If you don't do many lists of things, then it's fine. If you're doing massive crawling of the data offline in a batch mode, that's okay too. Those work really, really well. But a traditional application that, you know, needs related information that you want to show frequently to your end users, that can be very, very cumbersome to work with and slower. So relational sharding is basically defined by the developer. So relational sharding takes more understanding on your part to be able to do it. It's not that difficult, but basically what you're doing is you're actually looking at the relationships in the data and picking your shard keys and your relational strategy to shard based on things that make sense for your application. So it's specific to your application. It's not as automatic, but when you do it, it's really great. Why? Because related data is together. Related index data is together for most of your common queries. Not going to be for everything, but for most of your common queries. And when you do that, it can be tunable, and it's really like any other technique. If any of you have done index optimization and things like that with your databases, it's a similar kind of understanding that you need. It's not really that hard, but you do have to be aware of it. So let's just look at how database sharding works now with some examples. I'll show the way some of this works. If you're doing with a NoSQL database, it's pretty easy. What do you have in a NoSQL database? Put and get. Your API may vary, but that's pretty much what you have, right? And so the idea is you're putting in a key in an object. The key is used to shard by it, and the application can look at that and then put it in the right store. If you're doing a get, you pass in a key and it goes to the right place to read it out. Pretty simple how that works. If you're looking at relational sharding, let's look at how this actually works. This is a simple relational database. It's a bookstore model for bookstore orders. And so what we have is we're sharding by the customer. We call that our primary shard table. And the customers have orders and order items. Those are the books that they're actually buying. And so we want to be able to track all of that information. So those are what we call the shard child tables. So what we do is we pick one root or primary table, and basically all of the children of that we want to have in the same shard. So in other words, if I'm looking at customer 1, all of their orders and all of their order items should be in shard 1. I don't want them in 5 other shards. Right? If I look at customer 2, all of their information could be in a completely different shard area, and that would be fine. And so again, you can see immediately how we can retrieve information and get lists of rows of related information very, very quickly and conveniently because it's all where we need it. And the indexes, of course, go with all of this, right? Because we're just using a relational database technology, the indexes are all there as well. And you can, there are other ways to do this, but this is the key technique. Now, one of the things that happens, though, with a relational database is you have a lot of other tables that you have to join to, and you don't want to have to be going across shards to do those joins. As a matter of fact, we call that a cross-shard join, and we really think that that's pretty much illegal when you're talking about sharding. We don't allow it. So what we do is we actually make what we call global tables for all of your reference or your lookup tables. If you're familiar with the star schema type approach, it's something like that, where we take all the tables that are lookup tables, in this case country, publisher, book. They don't change as much as customer orders do. So what we can do is we can actually make those global, which means that those are written across all of the shards, so all of our joins still work. So what's the goal of relational sharding? To make it as efficient as possible and keep your relationships intact, right? Because again, the world is relational, at least the way I see it. So. All right, so how does this actually work? We basically do it with SQL. So we take a select statement, we can examine the select statement, see what the key is, bring a result set back. Again, that result set, if it's sharded, can actually come back direct from that particular shard. And if we do the same thing with writes, we look at the content of the write. If it's an insert statement or an update, we can actually look at that and determine which shard it's supposed to go to. So that's really the goal that we have here. And one other point I want to make here is the goal in a sharded system is that you have single shard reads and writes as much as possible. You can't have them 100% of the time, but you should go for having as many of those as possible. That's how you get true scalability and really, really high speeds. So that's really what we want is these are single shard reads and writes. So how does it look? If you look like at a select statement, select star from customer, where customer ID is 1234, we examine that key. The client can make the decision because it understands the sharding scheme, and it can actually go out to the right shard and get the information. If we're doing an insert, same kind of thing. We just look at that value or an update. We can do the same idea. So it's really very simple in principle how this works. But you do have to have some awareness of it, and you do have to analyze things up front and use your design tools to be able to do a good job and make sure that this is all clean. So what about multi-shard result sets? Because you can't always be single shard in an application. We haven't seen one yet that can run 100% that way. I actually had an application where we actually designed it, and we couldn't even do it 100%. We were pretty close, but not totally. So basically what happens is from the application server, what we want to be able to do is run something called a GoFish query. And what that means is, let's say we want to know how many customers bought a certain book last month. That's a good example of what we call a GoFish query. So what we do is we basically broadcast that query out to all of the shard servers. They run them in parallel, and then we have very clever aggregation techniques to actually bring the information back so that to the application it looks just like it's a single database. That's the goal. So again, this will happen, it's fine, right? But you want to have this be a smaller and smaller percentage. So we talked about optimizing over time with a database sharding technique. This is what you want to be able to do, is tune it over time so that you have fewer and fewer GoFish queries and more single shard queries. That's what will keep your performance great. So this is what an example of a GoFish query might look like. You know, give me all the customers, group them by country. That could be done in parallel very, very effectively. So it's kind of like almost like a MapReduce approach on the fly, if you think of it that way. So let's talk a little bit more about multi-shard result sets. Again, we talked about how they're scattered across, right? So a lot of what you're seeing in the NoSQL engines now, or the big data stores, is that you have to use MapReduce offline to be able to produce the results you need. And look, if you have big data and you have reports that need to be produced once a day or once an hour or something like that, it's fine to do that. There's no reason not to do that. You can do it offline. But if you want to do things you know, on the fly, and you want to be able to do things OLTP and mixed use, then relational sharding is much, much better. I just want to talk briefly about what we call the database sharding process. So there are steps to this that we've worked out. They're very simple, but they're important. The first one is you want to be able to analyze. So you want to look at your actual application and see if it's going to work with sharding. We have a concept with DB Shards called shard safety. So you want to make sure that your application is going to be shard safe when it runs. And we have various tools that help with that. So once you do your analysis, then you actually take your existing database and you have to shard it. So you need tools to actually take that database, and we call it, we have a loving term for this, which is the dump shard load process. So it's kind of like a rinse and spin in your washing machine. So basically we do take an existing database, we dump it, and then we actually break it into small pieces, and then we load it into the shard databases. And then you go ahead and manage it, and guess what? As you manage it, you find more things that you need to change because you find places to optimize. So you go back to analysis and you can reshard and expand your shards and all those kinds of things. So it's a cyclical kind of thing that never really stops through the life of the application. But of course, the biggest time you do this is the first time you do it. That's what takes the biggest time. And so we would love it if everybody started doing database sharding with a nice, clean, empty database, but that almost never happens. Right? So this is the process we go through. So what about high availability? This is very important in database sharding. Why? When you're adding shards, you're adding failure points. You're guaranteed to have more failures in the cloud if you shard your database than if you don't. It's just a guaranteed thing. So everybody's worried, of course, about failures if you have an outage. Right, everybody's worried about that. But what about maintenance? Like we said, you have to do maintenance on any kind of database, especially. The bigger it is, the harder it is to do. And one thing about sharding is it makes the maintenance much easier because why? You have smaller databases, so you can do a lot of things in parallel that you used to have to do all at once. So it makes it much, much easier to reindex or any of those kinds of things. So again, of course, an unplanned failure we're worried about, but make sure that you have a strategy to be able to do failovers for your maintenance tasks. We really say that this is important. We're also seeing more and more interest now in disaster recovery. So let's say between regions at Amazon would be a very, very important thing to do. But what about being able to do disaster recovery across clouds even? That would be really, really nice, right? Anybody remember last April with Amazon? Yeah, okay. So we saw that. We didn't lose any data. That was good, and we were up and running a lot quicker than most people. But you know, it was very painful for many sites were down for days. Actually, it was really, really difficult. So this is something we're putting more and more attention on. Also, the idea of having elastic shards. So you can do this to a degree, right? But don't think that your shards, so you know you can expand your shards over time and then you can contract them even if you have your volume goes down. Hardly ever happens, but we have had people ask. But what we do know is that don't plan on doing resharding, or what we call load balancing your shards, like every 5 minutes. Right? It's not going to be like app servers where you can have them just go up and down throughout the day. You can't really do that because data is big and it takes time to actually perform this. But you can do it over time. So let's say if you had something, an event happening weekly or monthly or something like that, that would be totally acceptable. You know, and again, with sharding, what's nice is you can start to see that you're running out of gas, and you can, you know, plan it in advance and then go ahead and reshard.
Can you accomplish that by, if you wanted to reduce the number of servers you're running on, putting multiple shards on a single instance?
Yeah, the question is, can you accomplish this by having multiple shards in a single instance? You certainly can, and some people do it that way, but we found that it doesn't really give you that much performance benefit or time savings. Yeah, it's really not, doesn't help all that much, actually. And one of the reasons is because a lot of the database engines don't let you copy a database from one server to another. Just point blank, you have to actually dump and load anyway, so it doesn't make that much difference. So just to summarize, database sharding is the most effective tool for scaling your database in the cloud, or anywhere for that matter. You can use it with any type of engine, again, SQL, NoSQL, column databases, caching. We really want to stress that you should try and use the best engine for the job. You're going to do much, much better at that and deliver much better performance overall. And again, ensure you have a very good high availability strategy that's proven and bulletproof.